All right, what I want to do today is look more at the birth and death of stars, and would like to get all the way through to the formation of the white dwarf, neutron star, and black hole as the end state in the evolution of a star's lifespan. And so this is most closely associated then with the subject matter from chapters 10 and 11 in your textbook, and of course you can check the section 3 homework to see what's due on the day of the midterm next week. And so just kind of a quick review of where we left off last time. We have the hydrogen fusion reaction in which for hydrogen, remember H is our symbol for hydrogen, and He is our symbol for helium. So we have 4 hydrogen turning to helium plus energy. There's a mass differential between the 4 hydrogen and the helium of about 1%. And so that mass is turned into energy by E equals mc squared. And so this gives rise then, if we look at the top screen, to an outward force that can balance the inward force due to gravity. And so those two tend to balance out in the case of our own sun when the core temperature is around 27 million degrees Fahrenheit, or about 15 million degrees centigrade. And so this process then is called hydrogen fusion. And when a star is in this state of hydrogen fusion, we call it a main sequence star. You know, there's a reason for this nomenclature, and that has to do with what happens when we plot the brightness of a star versus its surface temperature. And so if we do that, we plot the brightness versus the surface temperature. We find that stars that are brighter have a bigger surface temperature. And I think that would make sense. A more bright star would have a larger surface temperature. But this tends to plot in a logarithmic plot as a straight line. And so these are hydrogen burning stars that plot along what's called the main sequence. So put simply, this just means a brighter star has a higher surface temperature. But there's a certain relationship between them that plots linearly in a logarithmic plot. And we call that kind of a star a hydrogen burning star or a main sequence star. And so oftentimes I'll use the term main sequence kind of synonymously with hydrogen fusion and also more loosely hydrogen burning. So these are all terms that represent the conversion of hydrogen into helium, which is the main source of energy that a star uses to produce energy during the vast majority of its lifetime. So about 90% of the star's lifetime will be in this main sequence state where it's converting hydrogen to helium. Now, of course, and this is something we talked about last time, bigger stars have shorter lifetimes because their luminosity versus surface temperature is expanded. And so this is in a logarithmic plot. We see this linear relationship. But the brightness increases significantly for a really big star. For example, if we go and we look at this table, we see that a star here, M with a little circle next to it, is the mass of our sun. So if a star has a mass that's 25 times the mass of the sun, its surface temperature is 35,000 Kelvin, but its luminosity is 80,000 times the solar luminosity. And so it's time then on the main sequence, which means the time before it runs out of hydrogen in the core is only about 3 million years. Here's 10 to the 6 is a million. So this is 3 million. Okay. And so for a star like our own sun, the surface temperature much lower, only 6,000 Kelvin, luminosity of 1. So that's like its brightness. Okay, this is luminosity, how much energy it's putting out per unit time. And so its time on the main sequence would be 10,000 million years, or 10 billion. Okay, and so this is the time that our sun spends on the main sequence. It's an intermediate mass star. But then a lower mass star, like a red dwarf, would have an even lower surface temperature and a luminosity, only 3% the luminosity of our sun. But its time on the main sequence, 200,000 million years. Or when you do the math on that, that is 200 billion years, not million, sorry. 200 billion years. Okay, and so the bigger stars then are sometimes called O-type. Stars like our sun are G-type, and so there's a whole nomenclature for this, whereas red dwarfs are more like M-type stars. Now, I'm not going to make a big deal out of the nomenclature for the types of stars, other than to say that smaller stars have a lower surface temperature, lower mass, and a lower luminosity, whereas bigger stars have a higher mass, have a higher surface temperature, and a higher luminosity, which should make sense. The bigger stars are just, they burn brighter. But they burn up their material so fast that they die very quickly, even though there's more mass. They burn it up disproportionately fast, so that the big stars, the ones that might be, say, the size of from our sun to Saturn, they only live a few million years, and then they blow up. And so we're going to talk about the process by which they go through these stages, which ends in an explosion, in a few minutes. But the smaller red dwarf stars, which are maybe only half the mass of our sun, burn their hydrogen so slowly, very slow hydrogen burning, that they can have a main sequence lifetime where they're converting hydrogen into helium of 200 billion years. Okay, so our sun, as we said, about 10 billion, but a red dwarf star, 200 billion, but a really big O-type star, maybe only 3 million years before it runs out of energy. And so it's a little bit counterintuitive. You'd think the bigger star would last longer, but no, it's the exact opposite. So eventually then, as stars continue to live out their lifespan, they develop a larger and larger helium core, and this causes the star to heat up. And so again, this is the reason why we believe that all our oceans will eventually evaporate, because as the sun gets hotter, maybe 10% every billion years, eventually we get to the point where removing carbon dioxide from the atmosphere isn't going to help anymore. It's just going to be too hot, and our Earth will follow in the footsteps of Venus. What we think happened to Venus, all the oceans will evaporate, and the Earth will not be habitable the way it is today. But then finally, we reach the point where we get to the red giant stage, where 3 helium can combine together to form carbon. And so the red giant stage then happens, and this is just a review, but I think it's worth talking about, again, just to reinforce these ideas. When our sun turns into a red giant, which we think will happen perhaps in another 5 billion years, for our sun, then of course, for different stars, it'll take a different amount of time because stars that have different sizes have different lifespans, as we mentioned. That's all closely related to how much mass the star has initially. But here, with lots of energy being released, the red giant just keeps getting bigger. Keeps getting bigger and bigger and bigger. And we have helium fusion then happening in the core, which releases way more energy than was ever released before. And so at the end of this, maybe 1 to 10% of the main sequence lifetime, or the hydrogen burning lifetime, as we mentioned before, the star is in the red giant stage. Okay, so it's putting out lots of energy, and this, as we mentioned before, is when the inner planets will be engulfed. Okay, and so they'll be cooked and fried by the huge amount of energy that's being released in this latter stage of the star's lifespan. So if we go out now and we look at what the core is doing during this red giant stage, what we see is that there's a carbon core in the center. Okay, and so that's because that's the waste product from helium fusion. And then surrounding that carbon ash core, we have the helium burning shell. In the helium burning shell, you have 3 helium going into carbon plus energy that we mentioned a minute ago. And then surrounding that, the temperature is hot enough for hydrogen fusion to be taking place in the hydrogen burning shell. Because now we have enough temperature to burn some of the hydrogen that is out farther away from the center, from the core of the star. So we haven't really run out of hydrogen in the whole star. We've just run out of usable hydrogen in the core. But then once the red giant stage begins, the temperature in the core goes up by a factor of 10. So now we're at 100 million degrees. And now it's hot enough farther out in the star for the hydrogen burning shell to ignite. And that gives rise to basically a series of concentric shells that have the different reactions that have taken place in the star's lifetime up to that point. Okay, and so in the case of our own sun then, 1% to 10% of the main sequence lifetime for our sun, that'll be something like 100 million to 1 billion years. So our sun then will be in the red giant stage for, it's not a perfect science in terms of predicting how long this will happen, but it's somewhere between 1 and 10% of the main sequence lifetime, which is 10 billion years. So 1% of that is 100 million, and 10% of that is 1 billion. So somewhere in that range, that's how long it'll take for our sun to run out of helium in the core. So once that happens, then, and this will be true for any star too. It doesn't have to be our sun that we're talking about. All stars will go through this red giant stage. But once the star runs out of helium, this is after the red giant stage, so what's left then? What's a carbon core? and the star collapses again. But what does it leave behind? Does it leave behind something? Yes. It leaves behind what's called a planetary nebula. And so this is a way then in which we can identify what the nature of the stellar collapse is. If this thing has just gone through a red giant stage, then what we might expect to see is a kind of a halo of gas that's moving away from the dead star. And so this might be half the mass of the star that achieves escape velocity and becomes a planetary nebula. And then in the core, what will happen is that this is a carbon core now. If the mass of this carbon core is less than 1.4 times the mass of our sun, then it will become a white dwarf. Which is about the size of the Earth, and a density 10 to the 6 or 1,000,000 times the density of water. And so this is what we talked about last time again. You can double check the last lecture, but we have a shell of a electron pressure that stops the collapse of the star. Because all of the electrons repel each other, when it reaches about the size of the Earth. So it's a carbon core that's been smashed down to the size of the Earth. So we call this a white dwarf. And so this is what we expect to happen then if the mass of the carbon core is less than 1.4 times the mass of our sun. So if that's the case, it means it doesn't explode. The most exciting thing that'll happen to a star like our own sun, which of course is less than 1.4 times the mass of itself, is that there will be a huge red giant stage, and that'll engulf the inner planets. And so that'll be pretty exciting. A lot of energy will be produced by the red giant, which will make the outer planets somewhat habitable, perhaps for a short period of time, 100 million to 1 billion years. So that's a short period of time on a cosmological scale. It's a long time for us, of course. But the way that we could identify if a star has gone through these stages is to find the planetary nebula. And so here is a great look at what kind of our classic planetary nebula looks like. This is called the Ring Nebula in the constellation of Lyra. And so we see then that something like half the mass of the star is lost because the escape of the material from the red giant gives those particles enough speed so that they just keep flying apart. They never come back. Gravity isn't enough to pull them back in. And so what we'll end up with then is this big kind of perhaps spherical halo that surrounds a white dwarf. Now the white dwarf doesn't put out much energy, but we could expect a white dwarf to be somewhere right in the center. So if we see a big planetary nebula like this, then we know that there is undoubtedly a white dwarf somewhere in the center. And so that's one possibility then for the death of a star. And so the majority of stars then will end up like this, because the majority of stars have a mass that's less than about 1.4 times the mass of our sun once the carbon core has formed. However, if the mass of the carbon core is less than 3 solar masses and greater than 1.4 solar masses, then a new kind of process can occur in which the electron shell pressure that we talked about for the white dwarf is overcome. So there's enough gravity basically to crush the electron shell. Like breaking the shell of an egg. And so that means then that carbon is not the last state of matter that this star can have, but rather it can start turning into even heavier elements. Now I should mention here that this crystallized carbon core would be like a diamond, because it would be crystallized carbon in its most compact state. So imagine then a diamond ring that has the mass of the sun. Okay, and that's really what we're talking about here. A gigantic diamond. That's what these white dwarfs, that's what our sun is going to turn into, is one huge diamond. Okay, with this crystalline carbon structure that is something like 1,000,000 times the density of water. Okay, but it'd be perfect crystalline structure, it'd be like a perfect diamond. Okay. But as gravity breaks the electron shell, then it's possible for the carbon core to collapse further. But only if the mass of the carbon core is in this range from 1.4 times the mass of the sun to about 3 times the mass of the sun. Okay. And so what if it's greater than this? Well, then a lot of the things that I've talked about here will also apply. So we want to save this for also, call this case 1 if we want. We can call this case 2. This will eventually form a neutron star. Okay, and so that's where we're going with this. That before we can get to the neutron star, we have to go through some fusion processes that build heavier and heavier elements. So here's case 2 continued. So in the core then, it collapses more and then heats up more until the next kind of fusion reaction can take place. So what would carbon fusion look like? Well, it would be carbon plus helium going to oxygen plus energy. Okay, And so we could make oxygen then in the next stage. But then we run out of oxygen. Just the same ways we ran out of helium during the red giant stage, and we produced carbon. Now, I should say we run out of carbon here. We'll run out of oxygen in a second. But when we run out of carbon, then we'll have an oxygen core. And so then the oxygen core will collapse. Then oxygen plus helium would go to neon. So basically what we're doing here is we're just leapfrogging by 2 on the periodic table. Carbon is element number 6, helium is element number 2, so oxygen is element number 8 on the periodic table. 8 plus 2 is 10. Neon is number 10 on the periodic table, meaning it has 10 protons in the nucleus. Then we'll run out of neon. And this process continues on until we get to the formation of an iron core. And so here we could have chromium plus helium. Chromium is an element that is 2 below iron on the periodic table. So this would give rise to iron plus energy. And this is the end of the line. So this is chromium. This is element number 24 on the periodic table, meaning 24 protons in the nucleus. Helium is element number 2 on the periodic table. Iron is element number 26 on the periodic table. So here, this is like element number 6 plus 2 is 8. Here, this is 8 plus 2 is 10. Okay? And so this process then continues where the product of the previous reaction, the byproduct of that, becomes, it's the waste product from the previous reaction, but then it becomes the fuel that powers the sun in the next stage, until finally we get to iron. Okay? And so the iron core forms. And so that means that we don't necessarily just have one reaction going on at a time, but rather we have all of these reactions taking place in concentric spherical shells, just as was the case with the helium turning to carbon, remember, for the red giant stage, and then the hydrogen turning to helium in the shell that was outside of that. So now basically, if we look again up at the data projector, what we see is this is a little bit later on in the evolution of a star. Notice that the red giant could still be happening because these reactions are happening so fast in the core that the outside surface of the sun may not even have time to react to these. And so this is a greatly sped up life cycle that we talked about before for very big stars. Now, just because the star has a carbon core that's between 1.4 and 3 times the mass of the sun doesn't mean that was the original mass of the star. The original mass of the star might have been 8 times the mass of the sun for it to start to do what we're talking about here. And so here then we would have a helium fusing shell. Then we'd have a carbon-oxygen core in which carbon fusion was happening, and then oxygen was sinking to the center. And so now, in this next stage, we're going farther along. So here we have the hydrogen fusing shell, the helium, the carbon fusing shell. Here's the neon fusion. There's the oxygen fusion, and silicon fusion, all the way to the iron core. Okay, and so the iron core then is the end of the road for this star. Once it gets to iron, that kills stars. If we wanted to kill our own sun, all we would have to do is administer properly a sufficient amount of iron, and we could make our sun explode. Okay? And so with that thought in mind, the iron core is basically a point of instability for the star. So once we get to the iron core, this process ends, this process of fusion. Why? Because iron is the most stable element in the universe. And so every other element is like an iron wannabe. And so elements that are smaller than iron want to become iron by fusion, and that releases energy. But then also from above, if you have a fission reaction, something like uranium breaking down, it wants to become iron from the other direction. So that's why you can get energy from breaking atoms apart in a fission reaction, and also combining atoms together in a fusion reaction. And so if iron is the most stable element, that means that iron fusion doesn't release energy, it absorbs energy. If there's no energy release, there's nothing to fight against gravity. So let's remind ourselves of how this works. You've got an outward force due to nuclear fusion, and you've got an inward force due to gravity. And this is what balances out a star. But what happens if you take away the outward arrows, the fusion arrows? That means that the only arrows left are the gravity, the crushing forces. So once the iron core forms, it collapses. And so that's what happens then. We've got all these other fusion shells that surround the iron core. But once we've produced a sufficient amount of iron in the iron core, then when we try to fuse iron into still heavier elements, it absorbs energy. It doesn't release energy. And so that means that the iron core will collapse. Okay? And so if the iron core collapses, then basically it smashes down until it reaches about the size of a city. So let's take a look at that here. So now, the iron core is smashing down so much that it's no longer iron anymore. It crushes down to the point to where the protons and electrons are literally turned into neutrons. And the repulsion between the neutrons stops the collapse of the iron core when it reaches about the size of a city. So we'll actually call it a neutron star. So by the size of a city then, I'm talking about maybe 5 miles across or so. Maybe 10 miles across at the most. But this thing has a mass that might be 1,000,000 times the mass of the Earth, because this would be in a range of about 1.4 solar masses to 3 solar masses. This iron core collapses. It crushes down, but now it's being supported by the neutrons. So the neutrons also exert a pressure. So it's the neutron pressure that keeps it from collapsing all the way down to become a black hole. Okay, so it stops when it reaches the size of a city. Now, it may not seem like neutrons would repel each other, but they do. So this is a very compressed and strange state of matter. So we have then a neutron star. So remember, this is when the mass was less than 3 times the mass of our sun for the carbon core, but greater than 1.4 times the mass of our sun. So when this happens, then a neutron star is formed. And so, but the density is incredible. We said before that for a white dwarf, you have a density that's maybe 1,000,000 times the density of water. But for the neutron star, you took, say, an amount of mass that's equal to the Empire State Building, and you crush it down to neutron star density, you're looking at something that is about this big, about as big as this pen cap, okay? And so just imagine then taking the whole Empire State Building and smashing it down to something that has this kind of physical extent. And so you're talking then about something like a tablespoon of this stuff would weigh 100 million tons. On the Earth. And so this is incredibly compressed matter then that has formed this neutron star. But that's not the end of the story. The neutron star forms from the collapsed iron core. But what about all that other stuff that was going around the neutron core? Remember, we had all those shells of material, had the helium fusing shell, the carbon fusing shell, the oxygen fusing shell. All of a sudden, it's not hot enough for them to do their fusion reaction. And so the rest of the star starts to fall inward, imploding toward the neutron star. And so these particles then get going really fast. Then there's a rebound effect. Now you'd think, if you were thinking about this carefully, that the rebound wouldn't bring the particles out any farther than they were to begin with. It's like a ball being bounced off a surface. The farthest it could go would be the same height. But there is something that triggers accelerated expansion, and that's the production of ghostly particles called neutrinos. And normally these neutrinos don't interact much with regular matter, but neutrinos are produced during the implosion. And this drives the star outward so that these collapsing particles then are driven outwards. and they become what we call a supernova explosion. So the implosion then, upon the production of neutrinos, drives a catastrophic explosion called a supernova. Now, supernova explosions are gigantic explosions. If we had, say, a star, if our sun went supernova, and it won't because, as we saw, it doesn't have enough mass to do that. But if it went supernova, not only would the Earth be destroyed, the Earth would be vaporized. You wouldn't be able to find any of it anymore. It would be completely turned into just atoms. If Alpha Centauri went supernova at 4 light years away, that's our nearest star outside of the sun, it would take 4 years for the shock wave to hit us. But when it did, it would be like a nuclear explosion going off on the entire side of the planet that faced toward Alpha Centauri. Okay, and so that's how powerful these supernova explosions are. And we're kind of lucky in a way that we haven't been affected by nearby supernova explosions in the past. The Earth has dodged a lot of bullets in its 4.5 billion years of existence. But one of the reasons why that is even possible is that the stars are so far apart from each other on the average. And these kind of stars that are this massive to begin with are somewhat unusual. And also, when they form, they blow up quite quickly, because we saw that big stars blow up faster than smaller stars do. So they blew up a long time ago if they formed the same time that the Earth and our solar system did. And so that's another reason why we don't expect to see a lot of supernova explosions nearby. But maybe just enough, because when these stars blow up, they produce the heavy elements that make life possible on the Earth. Okay, and so the supernova then, as we mentioned before in a previous lecture, creates a shock wave What does that shock wave do? Well, it can disturb the intergalactic medium and cause new stars to start to form. But these solar systems are not quite like the ones in the previous generation because they're enriched with heavy elements. So as the intergalactic medium becomes more and more enriched with heavy elements, we have more and better chances for life to exist because now we have more complex elements. So this is basically the cauldron that is these exploding supernova explosions that synthesizes the heavy elements that makes life possible. And then normally you go, well, how are we ever going to get these things outside of the sun? But it's a supernova, so that's how you do it. Nature's got it perfectly figured out so that the supernova explosion automatically delivers these heavy elements to the intergalactic medium so that new generations of stars can form. So again, looks like nature knows what it's doing. And so if we look then at, okay, here again is just before the supernova, you can see a whole bunch of these different fusion reactions, basically a library of all of the previous fusion reactions that have occur in concentric shells that surround the iron core. And the iron core will collapse, and so then the rest of these layers of the star fall inward toward the iron core, bounce off of it, and this is the kind of supernova then that we would expect, what's called a type 2 supernova. Okay, there's also type 1, in which mass from a nearby white dwarf can push a star over the limit, over the 1.4 solar mass limit, and can give rise to a quick detonation of the carbon core. But the kind that we're talking about here is called a type 2 supernova, which the heavier elements are formed on the inside, and the iron core will form, and then you have the catastrophic explosion. And so here then, in the wake of that, is the Eagle Nebula here. And we can see that at the edge of the shockwave front, this is where new solar systems are being formed. And so this is like a stellar nursery that is driven by the energy of the supernova blasts that produce these heavier elements. And so this is where new generations of stars are forming. Here are a couple of other blast patterns from a supernova explosion.